Hey guys, welcome back to my channel. In this video is actually a continuation to my earlier video where I have trained a model using linear regression. Okay, so in this video, what we are going to do, we are going to do the residual analysis, and we will test our model on test data. Okay, so in yesterday's video, I have splitted my data into train and test model. Into train and test. So in this video, we will use that test data and also evaluate our model using that test data. Okay. What residual basically means when we train a model, okay? So, we can generally make a statement like no model is 100% accurate, okay? So, the prediction of the model may differ or differs from the actual value. Suppose the actual value is 10, so you might get like 9, 9.5 or 9.7 kind of values. The difference between the actual value and the predicted value is residual. Okay, that's what we call a residual. And to make yourself clear, residual is not a problem. So if there is a residual and it's normally distributed, or it's like equivalent, like you are getting 0.5 0.5 everywhere, it's like normally distributed, then it's not a issue. There are residuals in the trained model. Okay, so how to see that trend of that residual, how to do the residual analysis, we are going to see in this video. Okay, so let's go ahead. So as you have seen in my previous video, I have splitted my data into train and test. So just to revise, let me go back and let me come up here. Yeah, this line number 11, cell number 11. You can see I have used this train test split function, and we have splitted the data into train and test. So this is our test part, the x train, and this is our test part, x test and y test, and this is our train part, x train and y train. Okay, so we have trained our model on this training part, and now we are going to test on this test part. Okay, so let's come back here. Where were we? Yeah, here. Okay, so let's do a prediction using our model. So yesterday when we have trained our model, if you remember, we have kept it in a variable called LR. So if I go back and see, you can see we have taken LR variable and we have trained our model and fitted our model and stored into a variable called LR. Okay, so now what we can do, you can use now we can use this LR variable to make prediction. Okay, so in this line, what we are doing, cell number 19, what we are doing, like we are predicting the values which is there present in the train data set, and we are storing it in here y train pred. Okay, so we are storing the values, predicted values in this y train pred. Okay, let me print y train pred just to show you how it look like. Okay, so I will say print y train pred. Okay, y train pred, and let me see. So this is the value of y train pred. So these all are the predictions, and these all are the input. This is the prediction. Okay, so now what is the formula of residual? I just told you it's the difference between the actual value and the predicted value. Okay, so what is the actual value and what is the predicted value? The difference is nothing but our residual. Okay, so now to see it visually, or to see visualize it, we will draw a graph. And for graph, I have already told that we have a library called matplotlib. So we will initialize by saying figure equal to matplotlib, have a class like plt, and plt.figure we call to initialize a figure. Okay, then we use SNS library to use dist plot. Disk plot is not disk plot is like distribution plot. So I told you like residual should be normally distributed. So that's the function name suggests. Disk plot, distribution plot is the function name, and here you pass the residual, and bins is equal to 15. What do we mean by bin? So bin, basically you see this horizontal column like structure is bin. So if you count this 1 2 3, it should be 15. So this is the number of bin. Okay, so depending upon your data, depending upon the amount of data, you can adjust the number of bins. Okay. In third, this line is basically to give the title to the chart. So if you can see the error terms, the title which is coming is from this line. We are setting the title. Okay, and we have setting the font size. Now we are printing this label, this below label by this line, and we are showing the graph. Okay, now let's come to observation. So you can see the graph. This is the graph of the residual distribution. So you can see center of this curve is nearby 0. Okay, it's like if you draw a imaginary straight line here, you can see it's like nearby 0, which is a good sign. So we can say residual is normally distributed, and we are all green, we are all good. Okay, now second thing we can observe is like pattern in our residual. Okay, so to visualize the pattern, we use the scatter plot. Yesterday we have also used this graph to see the data point. Okay, now in this video we will use this graph to see the residuals. Okay, on the extreme. Okay, let me rerun this. I have already run the code. Okay, so here you can see there is no any such patterns in this data. What I mean, the data is equally distributed over all areas. There is not if you can see there are many dots, or if you have observed this part is blank and this part is full of data points, that should be area of concern. But for now the data is equally distributed over here. If you imagine like a virtual line between this 0, a horizontal line here like this, so you can see all the data points are seems to be equally distributed, so we are all good. Okay, now let's come to predictions. So what we'll do, we will do predictions on the test model. Okay, so if you remember, yes, in yesterday's video I have told you that stats model doesn't add the intercept by default, and we have to use that add constant method. So same we have done here. Okay, let me run without this. Let me run with this x test. Okay, x test. Now let me run this. Yeah, we were expecting this here. See what is saying, shape 1602 not aligned with dimension 1 not equal to 2. Okay, why it's saying? Because yesterday we saw the formula of linear regression, and the formula was something like this. Okay, y equal to c is the intercept, plus m1 is the coefficient of your first predictive variable into our predictive variables. Okay, so this was the formula, and by default the linear regression model doesn't include this c part. Okay, so using add constant method, we like add the c variable there. Okay, the intercept there. Okay, so let me go down. Okay, we were here, and let's pass the correct variable here, x test sm. Okay, so what is x test sm? Basically we are adding that intercept value and we are storing in this variable, and now we are passing to our model to predict the values. Okay, as you can see, as expected, we are getting no error. Okay, this I have printed just for the sake of like showing you how the prediction data look like. Okay, now for doing the evaluation of the model, we need certain libraries, or there are certain metrics on which we evaluate our model. First one and most important one is like I can say R2 score. So in linear regression, for this use case, we generally like see the R square, R square, yeah, R square score of the model, and the MSE score. MSE score is the mean squared error. Okay, what are these two? I'll talk in a bit. So let's go ahead and yeah, run this. Okay, we have like imported this library. First I will go with R square. So in R square we are just passing two values. First of all, the y test, which we got from train test and split function, and the y prediction. Okay, so this is the actual value, this is the predicted value. We are passing it to the R2 score, and we will get the R squared value. Here the R square is 0.79. Yet it means like 0.79% or 79% of the data our model is predicting, which is correct. Okay, so it's quite good number. And also there is a thumb rule. If you see, when we printed the summary of our model, when we trained our model and we printed the summary, we were getting this value. The R square value was 0.816. Why? Because this is the R square of the training data itself. It was not on test data. So in training data it was giving us 0.81, and the R square of the test data should be 5% range of this value. Okay, so you can consider the value. It should be like minus 5% to this value. So the 0.79 is a quite good number because it's fall in that 5% range. Okay, so R square we are clear with. Okay, now let's see this mean squared error. Okay, so what do we mean by like this mean squared error? So this is also a metric. This is also metric to measure the like average square distribution between the predicted value and the actual value, and it's a metric to like evaluate the efficiency of the model. Okay, and a mean square error should be lower than the variance of your target variable. Okay, so there are terms like variance of the target variable. What do you mean by the variance of the target variable? I will explain in some other videos because that will be too much theory here. Okay, so let's concentrate on the practical part here. So what MSE does is it's basically it's giving us a number 2.10, and if we see the variance of our target variable, I can simply write print. Okay, print advertising, and our target variable is sales, so I will write sales here, and dot var. So var will print the variance of the target variable. Okay, print this. So the variance is coming around 2.7. Okay, okay, let me pass here y test. What we get here? Okay, oh sorry, we can't do this. We can't pass directly to the y test. We have to pass it to the advertising, and you can see the variance value is 2.7 of the target variable, and the MSE value is 2, which is quite good. It's 4 basically. We are calculating the square root, so it's basically 4, which is also a good number because the variance is 27 and we are below the range, below the variance, and that's a good sign. Okay, now let's visualize the data of which we are predicting. So we plot the data in scatter plot, same as we did in our last video. For like uh, while we are preparing our data, we have prepared some pair plot there to see how data look like, the pattern of the data. Okay, now after on prediction on the test data set, we also draw the same graph to see the distribution, how the data look like. So let me come here. Where were we were here. Okay, so you can see It's also seems like good because everything is like seems to be normally distributed. The data points are hugging this center line, this line, okay, the center line. And we can't observe any patterns like data edge gathering in a particular area. It's like normally distributed to the start to the end. So we are at good side, like the model is performing really well. Okay, so hope you like this video. In next video I'm going to train our model using sklearn, and sklearn is basically the lighter version of this stats model. Okay, so in next video we'll see that how to train our model using sklearn.